Why should we use a microreactor to obtain kinetics? There are some obvious advantages. There are the same advantage than for production microreactor. First of all, we can very precisely adjust the residence time, the time for the reaction, and even the temperature. The other thing is, if you have a very fast reaction, you can do a lot of experiments in your laboratory if you use lab automation. That saves you a lot of time and even some material. The other thing is that with a continuous reactor, it's very easy to implement online analytics.
So the experimental results show that for high flow rates above 30 milliliters per minute, we also have a very good mixing performance of the T-mixer. And with regard to the scale-up, this means that we can safely assume short mixing time for both reactors at low flow rates in the micromixer and at the aimed higher flow rates in the production reactor. In this case, short mixing time means shorter than 1 second, which is clearly shorter than the characteristic time of the Michael addition. So in the scale-up, we have a transfer to an entirely different mixing principle, but with similar mixing performance at the operating points. Now the last point is the heat transfer. As we had shown, characteristic time for heat transfer strongly depends on the channel diameter, and the scale-up to a larger channel diameter always comes with a reduced ability of heat removal. But since we can simulate both reactors with our model in DynoChem, it is possible to predict the reaction progress in both reactors by taking the reduced heat transfer coefficient and the reduced specific surface into account. Now these figures shows the change of temperature and conversion profiles in our scale-up example. The production reactor, that is a solid line in this figure, has a much more pronounced hotspot at the reactor entrance region. And the difference between maximum temperature in micromixer and production reactor is about 20 Kelvin. But however, when we compare the conversion in both reactors, there's only a slight deviation. And for this operating point, the production rate in the reactor is about 2 kilograms per hour. Higher flow rates are possible in the reactor, but this would require different equipment and large amount of the reactants. With regard to the small reactor volume, an extremely high space-time yield results, which is characteristic for micro and milliscale flow reactors. So as you can see, the obtained yields are close to the predicted curve and also close to experimental data from our experiments with the microreactor. So as a result, the assumptions and predictions of the scale-up approach are confirmed by experimental data. We could confirm that mass transfer limitations do not influence the total reaction rate and that a lower heat transfer in the production reactor does not lead to problems in reaction control. But as I mentioned before, another reaction with a higher activation energy would possibly require a different reactor concept. And one possibility for that, one that we tested and simulated, is a reactor module where one reaction stream is split in several partial flows. Now in this case, reactant B is split into 4 equal parts that are added into the reaction channel at different locations. And this way, the large hotspot at the entrance regions of the reactor is reduced into 4 smaller hotspots. With this multi-injection reactor module, the hotspot of the Michael addition could be reduced by approximately 15 Kelvin, and for a strongly temperature-dependent reaction, this could be crucial for reaction control. Finally, I would like to summarize the webinar with some conclusions. Microreactor setups can be a powerful tool for kinetic studies and process development, since experimental data can be generated easily and very efficiently. However, there are important experimental requirements that have to be considered carefully, because otherwise the determined kinetic parameters can be falsified by transport phenomena such as backmixing or the formation of a local hotspot. In order to ensure the validity of the applied reactor model, we suggested some experimental methods for characterizing the reactors. And so if the described requirements are fulfilled, DynoChem can be used for fitting, optimizing, and for scale-up considerations. For the scale-up from microreactors to larger flow reactors, we would like to point out that if validity of the applied plug flow model is confirmed for both microreactor and production reactor, the Carbot model of heat and mass transfer can be used to predict scale-up effects. And this is, of course, very helpful, especially for predicting the temperature profile in a production reactor, since reduced heat transfer might be a limiting aspect in scale-up. And in our opinion, a great advantage with this approach is that geometric similarity is not necessary for the scale-up, provided that ideal plug flow behavior and good mixing performance is given for all considered reactors.